All right, so I guess everybody is here still, nobody left. Maybe we wait a couple of minutes. I wanted to show some videos about superconductors. For practical purposes. For example, this guy here, he made a magnetic track. So you guys are going to see these squares in this video. These little squares mean that these squares are magnetized like this. Okay, so they are magnetic field goes from below to up. Okay, and each one of these little squares here. Okay, and he will put a superconductor on top of this magnetic track. And as we saw before, the superconductor doesn't like this magnetic trap. So let's see what happens. Let's watch. Let's the video. So that black piece you saw was the superconductor. This is the magnetic track. This is a metallic film. You see that it's a metal, right? So metal magnetizes it gets magnetized, right? It's a very cool experiment. Make round two circles. Pretty much round. A bit on the cheese, but anyway. Yeah. Then he has a magnetic track, right? Now he takes liquid nitrogen, and this black disc, this is the superconductor. This is one of the key materials that we have. And as it cools down, it becomes superconductor. Look at this. And what happens, you have magnetic levitation. This phenomenon is called magnetic levitation. So because the superconductor is trapped inside this field, it's very stable. So he puts these green films there to show the magnetic field, magnetic gradient. Yeah. And as long as the superconductor is cold, it stays there fine, you know. It's very stable. Very stable. Until it warms up and falls. Then you have to put back on liquid nitrogen. I did this experiment myself. It's very nice. Now he's doing the exercise of putting opposite, the magnetic line opposite. So in this case, you see that each of these blocks to stay closely like they are, they have to be opposite. If this one is up, the next one is down. If this one is up, the next one is down. You know, so it's like, let me put here in the middle, is better, like up, down, up, down. So in between them, a zone where there is zero magnetic field, right? Because you have to flip from minus to plus. So in between them, there is zero. But actually, there is a little trap there. It's this where you have either up or down. The superconductor will try to be these traps. Okay. Yeah. They make this up and down pattern. Put conductor, and now is this trap is not like that. It has to be fixed in some point, not like in the other case, right? Yeah. So this is the phenomenon of magnetic levitation. Very stable, very powerful. By the way, this is heavy. Yeah? This material is heavy. Now he takes the magnet, puts on top of the superconductor, and pushes it. You see that even upside down, it's in the magnetic field. It's very weird. It's not magic. It's just quantum mechanics. Yeah, yeah. Interesting. For me, this is when this first time I was crazy, going crazy. And actually, uh, in China now, China, Japan, Germany, they implement this project of the so-called maglev, right? Mag train. It's magnetic levitating train. This is pretty much like an airplane. This train goes and it can reach like 550 meters per hour. It goes like airplane velocity, but it goes rail. It's ultra fast. I think in Shanghai from the airport to the center of Shanghai, they do this in 7 minutes. It used to be 1 hour train. Now it's 7 minutes. It's something ridiculous. That little principle of magnetic levitation in the lab, with the magnets, you can go to like and make some billions of dollars investment. And with the good engineers, you can actually, yeah, till 100 kilometers per hour. It runs on wheels, and it's pretty much electric currents that accelerate. After 100 kilometers per hour, it starts flying. The wheels are off, and it's just levitating, and then it's getting pushed from the electric. It's the electromagnets who produce the push forward. The superconducting part of the train is just helping it to fly above the rails, and the electromagnet is pushing forward. Okay, things starts going airplane speed, very fast. So this is one of the applications of superconductivity. It's quite nice. Let's move for the top speed. Top speed 431 kilometers per hour. Things starts looking blurry, right? Fast, and it starts deaccelerating. So in 7 minutes, you see, it got to the destination. So this video is almost 8 long. That's the time to go from, I think it's from some faraway part from Shanghai to the city center, something like that, or vice versa. This is ridiculous top speed. Here's another. school experiment, but I don't think they do something new. Yeah, it's the experiment, right? Yeah, the disc levitating. Ah, they put discs. Yeah. Of course, we don't want two trains. Yeah. The question is, how doesn't the train fall the side? You see, here, for example, in this trail, they put two rails, two magnet rails, one on the side of the other, and the disc on the middle. So this maintains the stability of the rail. But actually, in the superconducting train, is way more complicated. I think I have a video. I think there is a video on YouTube about this. Um, it's the Japanese maglev. I think in the video for Japanese maglev, they have this, yeah, this train here. There's all these details. How there is the guide magnet. You know, it's some kind of trap they built. So the passenger cabin is here on top, and they put actually these electromagnets here, red and blue, to push it forward, right? And there is this magnet here on the side, here and here, and these magnets make the train stable on the center of the rail. So they push to the center. That's pretty much how they maintain stability. So stability up, stability to the side, and it's pretty much safe. Yeah. There was another part here. It was quite interesting. But yeah, interesting, right? Yeah, I think they are doing now in Japan this line from Osaka, Nagoya to Tokyo. So it will be more than 400 kilometers long line, and by 2027 to Nagoya will be ready. So maybe one of you guys can go there and check yourself by 2027. In 2037, I hope we are all alive and we'll go for Osaka. We can go for Osaka from Tokyo to Osaka. This will take not much. If it's 400 kilometers and the top speed is 430 kilometers per hour. Let's put top speed 200 kilometers per hour, right? So this will take half an hour to go from Tokyo to Osaka by maglev. You know, it's ridiculous speed, very fast. We don't even have any like this in modern days in the floor. You know, maybe by airplane, yes, but trains, no, we don't have anything like this. Okay. So this is one of the applications of superconductors. Is this magnetic levitation? There is also the application on quantum computers. There are also applications on particle accelerators, because you saw that we can guide this. Wait, why is this thing blurred? Yeah, don't understand. Yeah, you saw that there is this strap right on the train here to stable, and it works the same with particles. So, for example, in these particle accelerators at CERN, they have pretty much the same trap, and instead of train, they put protons on the. What is it? I lost. But anyway, so in particle accelerator superconductor, if you put here, I think they should mention somewhere that there are traps that guide the particles. Anyway, yeah, superconductivity accelerators. I think this is the film. I just wanted to show more or less how they look like. Yeah, so in particle accelerator, you have this very long tubes, and the particles circulate around and collide. So you send a lot of protons, for example, very fast protons at 99.99% of speed of light. They collide against each other, and they meet up. For example, in CERN in Switzerland, this rail is of the size of a city. So there's all these rails, and each now and then, let admit somebody else. Yeah, every now and then, the particles collide, and they make measurements about the collision of particles. So this rail, to get them also in a stable trajectory, 99% of light, speed of light, they need some superconducting traps. Now it's not the superconductor who is trapped in the magnetic field, it's the trap of the superconductor who traps the particles. So the particles, they interact with the superconductor. When they are very fast, they produce some magnetic field around them, and then superconductors avoid them. So they just keep on the center of this cylinder, and they keep rotating very fast. So they rotate and collide at some point. So there is some part of the trap where they put all these. Look at the size of. By the way, this is a person, and this is the machine to make the measurements. So just so you have an idea of the size of these tunnels and how these particles collide. Yeah, so also applications for superconductors is making these rails for particles. Okay, so that's also interesting for me. I was there in CERN. I visited, and it's quite impressive machinery. Okay, nice. Now I will quickly go. Okay, not go too deep into these problems of Maxwell equations. Maybe it's not important. So if it's too boring, we will just skip this stuff and continue our lives. But I'm having some bug, and this thing is not appearing. I don't understand. Maybe I have to wait a second. Maybe I do like this. Okay. So as we saw, we talked about electric field. We talked about a lot about magnetic field, right? We talked a lot about charges. We talked about currents, right? So what governs all of this? Maxwell equations. So in our approach here, this will be some cherry in the cake. Okay, talking about Maxwell equations, not the center point of the course, of course, but to have a feeling what is the mathematical formulations that appear in superconductors. Okay, in conductors in general and superconductors as well. So in these equations, Maxwell equations, we will involve electric field, magnetic field, charge density, current density. There will be some fundamental constants. Okay, so in international system of units, it will appear this first constant, this permissivity of free space. Okay, epsilon 0. Units doesn't matter much. I will just skip the discussion about units, Faraday per meter, right? Or this. There is also the magnetic permeability of free space. This is another fundamental concept that appears. Okay, so it's this value, Newton ampere. Okay, and how they look. Okay, in both system of units. So I pretty much will focus on GS units. So we have this first two law, Gauss law for electric field and magnetic field. So again, we use differential operators, right? So divergence of E, I'm using this differential operation gradient. I ask you guys if you have this course, so you confirm that some of you understand. So who doesn't understand, this is not fundamental, just bear with me. So divergence of E, 4 pi rho. Okay, so if you have some distribution of charge, rho, some extra electrons or extra protons, it means you're missing electrons, okay? It will produce some electric field, all right? And in the case of magnetic field, you never have extra north pole of the magnet or south pole. You always finish. So in the magnetic particles, always the magnetic field appear in some end and ends in another point. So here is of the magnet, here is south of the magnet, and it always the field lines always start and end at the same point. Okay, so it means that divergence, this translates mathematically into this law, divergence of B equal to 0. So these are the two Maxwell equations. There is also this equation, Faraday law, okay? Checked before, right? But basically the idea here is that if you put a piece of conductor, for example, a copper, right? If it's circular like this, and then you apply some magnetic field penetrating this circle, okay? You apply some magnetic field like this, and have change in time. For example, this magnetic field is oscillating. What are you going to see? You're going to see a voltage appearing along this loop here, along this wire. It will be some time-dependent voltage appearing because you apply some magnetic field, which is dependent on time as well. Okay, that's what this law deals with. So I will not go into much further details. Okay, but here it appears, first tip is that it appears speed of light. It has to do with our system of units, and there is this important and last, also so important and last Maxwell equation, the Ampere law. Okay, so Ampere law tells that the rotor magnetic field minus 1 over c time derivative of electric field. This is 4 over c times current. Okay, there is even a very, very famous, let's see a question here. Can there be another E? Nabla E. Yeah, maybe you're expecting the SE units. Maybe you're expecting this equation. This is what you mean. Let's see if I understand your question correctly. Ah, I see. So it doesn't have to be. I think your question now. I think you want to know um, if we are not in vacuum, right? So as I think I put this, I think I put this in the previous slide. Uh, this is from permissivity of free space. It means this works in vacuum. These constants here, they are in vacuum. But if you are in medium, these constants will change, right? So this is a good question. This epsilon zero appear here, and mu zero that appear here. This is in SE units. So these are on the left side of the slide are the equations in SE units, and on the right side of this is the equations in CGS units. So CGS means we work with centimeter for space, gram mass, and S second for time, right? In SE, we work meter, kilogram, second, right? So usually in superconductivity, in theoretical stuff in superconductivity, usually don't go for SE. Some guys who SE, they usually are experimentalists, and they we prefer to keep in SE. But theoreticians, we like symmetry. And CGS brings symmetry to the equations. Okay, so this is why we just keep this form on the right here. By the way, if you use CGS, instead of having two fundamental constants, instead of having mu0 and epsilon 0, now you get only one fundamental constant, which is speed of light, c. Okay, so this is the advantage using using CGS units. I recommend. I like myself. I really like this idea. I think like Einstein, because people wanted to abandon electromagnetic. People wanted to abandon Maxwell equations to keep Newton's law, and Einstein was the guy who kept Maxwell equations and abandoned Newton's law and built the relativity theory. Actually, he was very successful by obeying Maxwell equations. So I try to be respectful to Maxwell equations, and I feel that in Maxwell equations there is something very important that appears in relativity is this light. Okay, so speed of light here where that appears, and simplifies the theory because now you only have to measure one fundamental constant. Okay, so Maxwell himself discovered that after some manipulations, manipulating these equations, so you can isolate out electric field, for example, in one of these equations, and taking water and blah 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 and making manipulations, you get to the wave equation. So this equation in SE, okay, this is, for example, because we have rotor of E, this came from Faraday's law. If you take Faraday's law, take blah blah blah, make some manipulations, what you will get exactly this equation for the magnetic field. Okay, and this equation is a so-called wave equation. So look at wave equation, Laplacian of some quantity, okay, the wave amplitude, for example. Laplacian of this quantity is equal 1 over speed squared times second derivative of this quantity. This is a so-called wave equation. And solutions of these equations are sines and cosines. Okay, so the harmonic oscillators and so on. So maybe in school you studied harmonic oscillators, right? They appear because of these kind of equations. And what happens is that Maxwell himself, he made manipulations on these equations and found that electric field and magnetic field, they obey the wave equation. And what appears in the wave equation is this factor here in front of them, in front of both magnetic field and electric field, appears if you combine here the speed with the speed of the wave with this use epsilon 0 mu 0, you will see that 1 over c squared is epsilon 0 mu 0, right? So that he discovered, this is one of the first successes in physics, that he made the theoretical prediction, and when people measured the prediction, they confirmed. He actually calculated that this was the product. If you multiply epsilon 0 by mu 0 and take the square root and 1 over, take the inverse of this number, you should get the speed of light in vacuum. And actually, when they calculation, this is exactly what they measured. Okay, so they got this 3 times 10 power 8 meter per second speed of light. Okay, appears from that. But this is when you are in vacuum, right? When you're inside some material, you can have this density of charge, of current. Okay, and then Maxwell equation looks a little bit different. So let's check, for example, static regime where time derivatives are 0. So time derivative of electric field, time derivative of magnetic field are 0. It means that the Maxwell equation reduced to these 4 equations. So here we just the time derivative that should appear. So it should be here, right? 1 over c time derivative in E. This is 0, right? And same thing here should be 1 over c time derivative in B. Also 0, right? So by removing these terms, you get these equations. And yeah, there are these vector identities. Usually in the vector calculus courses, we learn these identities. Rotor of gradient is 0, right? Divergence of rotor is 0. Who doesn't know about this? Don't worry, just is a mathematical property of these differential operators, okay? Means that if rotor of electric field is 0, we can define some potential, some scalar function. Instead of a vector E, we can just consider some scalar function and take the gradient of this function. So if you define E minus gradient of this scalar potential, you get exactly this Maxwell equation. Okay, so rotor of E is 0, automatically satisfied if E is the gradient of some potential, of scalar potential. Then you reduced your electric field from 3 components, X component, Y component. You just reduced it to one scalar number, one scalar function. So it just has one component. Okay. And same thing with magnetic field, more or less same thing, is that the other equation was divergent of B equal to 0. This is always satisfied, right? Divergent of B is 0. And because the divergence of rotor is 0, you can always define B as the rotor of some vector potential. Okay? The potential, but in this case as vector. Okay? And because we define in terms of this vector potential, always the divergence of B will be 0. So this equation is automatically satisfied. So when you go and plug these two definitions here, when you plug definition and this definition into the equations before, into set of equations, what you get a new set of equations, just 2 equations. So you reduce from 4 equations to 2 equations in terms of the potential. So now it's scalar potential, now it's vector potential. But in this case, you increase the degree, the differential order of the equation. So now Maxwell equation looks second order. So now you have this rotor of rotor. Right? So now you have a pair of equations, but of second order. Previously, you had equations of first order. There is some kind of conservation here, mysterious conservation. Okay. So these are the so-called potentials. Okay. And these potentials, when you express this equation in terms of potentials, it appears some interesting property. Is what we call gauge invariance. So gauge invariance means that if now you define electric fields in terms of scalar potential and vector potential like this. So previously our definition like this showed that the equations was automatically obeyed. Maxwell equation was automatic, right? If you have that E is minus gradient of, it means when you take the divergent, the rotor of E, this will be minus rotor of the gradient of phi, which is automatically 0 because of a vector property of the operators. Okay, so if this thing is 0, it means that Maxwell equation is satisfied automatically, right? The point now is, let's try to make some modification and add here this minus 1 over c time derivative a. In this case, let's take, for example, this expression here. When you take rotor of E will be rotor of the gradient, which is automatically 0, times time derivative of this thing, which will be minus 1 over c time derivative of B, because rotor of A is B. This is B, as we defined before. It means that we recover Faraday's law, as it was out, not in the static regime, in the dynamic regime. Okay, so this means that we can play around with these potentials, and the equations will be invariant; they will not change. And I will go fast over this because it's not the key point of the lecture, right? So actually, in terms of potentials in general, even for dynamic case, okay, you have these equations looking like divergence of phi, divergence of the scalar potential, will be time derivative of divergence of A. And it will be this operator Laplace plus 1 over c squared time derivative. This is sometimes defined as the D'Alembertian operator, okay, named after the revolutionary of the French Revolution, right? D'Alembert. He studied this kind of operators, okay, wave operators. And so this kind of operators on plus gradient of the divergence time derivative equals this thing. So sorry for these long equations, but I just wanted to mention that Maxwell equations can be expressed in terms of potentials, and you can play around with these potentials. And just having into account that you have this definition here, the magnetic field and the electric field in terms of the potentials, you're safe. Maxwell equations are all obeyed. So you need to solve less equations. Again, these are only 2 equations. And your life is easier. Okay? So I will come up with a term now, gauge invariance, right? So what is gauge? According to the dictionary, gauge is an instrument that measures and gives a visual display of the amount, contents of something, right? So for example, sometimes you have a cup to cook something, and in this cup, there is this little lines to tell how much liquid you have here. So this little thing here is called gauge, okay? And the second meaning is thickness, size, capacity of something, you know? This, usually in guns, you have this stuff like gauge, shotgun, gauge 12, you know? There's this big shotgun that looks like this, and, you know, so this big shotgun, and they gauge 12, so it's very famous. So this is, but actually in electromagnetism, in Maxwell equation, gauge has a, oh, sorry, I missed some question here, like a speedometer. Yeah, the speedometer can be this little thing in the cars that you have. So you have these speeds in the car, and marks some speed here, right? That is the gauge, the quantity of something. For example, also in lakes, sometimes you have a lake, a dam, artificial lake, right? And they put a tower, and in this tower they put some lines to have an idea how much is the deepness of the lake, and they can more or less have an idea of how much water they separated in the lake. So this is also called gauge, okay? So it's something that tells the quantity of something that you have in your organized or saved somewhere, okay? So now let's make a game here. Let's say we change the vector potential with a gradient of something. So let's, this Greek letter is chi, okay? So let's call this scalar letter chi a gauge, okay? This is a fundamental concept in physics, especially in Maxwell equation, because if you sum your vector potential with gradient of something, it doesn't change the equations. For example, magnetic field, we define the rotor of vector potential. So if you take the rotor of vector potential now after summing this gradient, again, it's trivial. Because of the vector property that rotor of gradient is always 0, it means that this term doesn't account for magnetic field. You always have the same B, okay? So magnetic field is invariant under gauge transformations, okay? Also, when we subtract some derivative of the scalar potential like this, if you sum minus 1 over c time derivative of chi like this, the electric field is also invariant. So you have here, for example, minus gradient of phi minus 1 over c d of a prime. If you change this guy like this, you will see that the electric field is not changed. So let's put here the gauge on the scalar field, and the gauge again goes to the vector potential like this. So this is how vector potential is changed with the gauge, and this is how scalar potential is changed with the gauge. Again, pay attention that it's very funny how time derivatives and speed of light, they appear together in the equations because they correct the units. So gradient, the unit of gradient, is 1 over length. For example, 1 over centimeter, right? Gradient is derivative over x, right? Derivative over y. So it means that it has distance on the denominator below on the fraction, right? So the unit will be centimeter to minus 1. So to have the same units, so in this formula in CGS formulation, vector potential and scalar potential, they have the same units. It means that this term, it should also have units of 1 over centimeter. And this is actually true because 1 over c, right, times time derivative over time, right? So the units here, what is this? So unit of 1 over c, this is, c is meter per second, so this will be second per centimeter. And the unit of derivative, this will be 1 over second, right? So cancel second with second, this is 1 over centimeter as well. So you see that the symmetry in Maxwell's equations that appear with this definition, you know, this beautiful, beautiful. So CGS, I love CGS units. But anyway, I just wanted to show this term, gradient of time derivative here with the minus sign will cancel the term gradient with time derivative. You can permute these two operators, derivative and gradient. You can exchange for gradient time derivative when you have continuous functions. So as we are assuming that is a continuous function in space. Okay, so assuming this, you see that this guy will cancel with this guy, and then you have the normal definition for electric field, also invariant. And in general, Maxwell equations are also invariant. And there are many gauges in study. People study Maxwell equations in many forms. Okay, you have a lot of freedom. When you introduce these potentials, what you have is that you have a lot of freedom in these equations. It's like sometimes when you integrate something, you have a free constant after the integral. If the indefinite integral, you have a free constant there. So actually in Maxwell equations, I'm sorry, maybe it's too mathematical to discuss, but I just want to say that there are many different gauges. People work making transformations, right? So you can use this chi function to transform the potentials in the way that you want. The potentials change, but the electric field, magnetic field doesn't change. So chi, this function, it can produce, you can define it in such a way that divergence of vector potential is 0, or you can, this is called the Coulomb gauge. There's the Lorentz gauge, where the of A is plus 1 over C time derivative of scalar potential is 0, called Lorentz gauge. There is the Weyl gauge, okay, or time gauge, temporal gauge, so on, where scalar potential is 0. So this is very, very important one. I use, for example, in my research, I use Valeria is here now. She also knows about this stuff, right? There's the London gauge, right, where A obeys this constitutive relation. Actually, the vector potential is connected to the current, okay? And this is very mysterious gauge, but actually was the Broden Londons. There are two brothers, Heinz and Fritz London, very famous guys. I think it's like this who writes Fritz. So Heinz and Fritz London, they derived some set of equations to describe superconductors, and this electromagnetic theory that they formulated, it connects the vector potential with the current. Okay, so this is so-called London equation. For example, this is Maxwell equation in static case. So rotor of B is 4C J, right? But we have this London gauge where direct connection between A and J. So the point is, instead of working with A and J, we can do is we can take rotor of this first equation here. So we can take rotor again, rotor of J, rotor of A. And what we'll have this equation here. Rotor of B equals -1 over some characteristic distance called lambda, okay, or lambda L. This is the long penetration length. And using vector identity, another vector identity, right? So rotor of some vector will be equal to gradient of the divergence minus Laplacian. Okay. There is this another vector identity. It's not important, but the point is that this double rotor can be transformed into Laplacian. Okay, and then it means that Laplacian of magnetic field is equal to 1 over Laplacian times B, and lambda is given in terms of some constants that he defined inside his. Okay, so this constant is density of electrons that participate in the phenomenon of superconductivity, right? So if you have density of Cooper pairs, because Cooper pairs is made of 2 electrons, so actually this density of superconducting electrons is double of the density of Cooper pairs, right? E squared, this is the charge of the electron, and m is the mass of the electron, right? Here I think I put this home assignment, find the London equation for the electric field, but nada. I think this is, we don't need to go into this detail. So please neglect. I don't think we need this stuff. But I'm going to show now some very simple solution for if you're interested how to do this stuff. You can just go to the London gauge, right? You can use this equation here and substitute in the expression of electric field here. So you can consider phi equal to 0 and throw here your current. So instead of A, we saw that there is a relation that puts current here, right? With some proportionality constant here. So actually, the second London equation looks like this: that electric field inside the material is proportional to time derivative of the current. Okay, but you don't need to calculate this stuff. Okay, so quickly doing here, we have this equation, right? Lambda of B equals 1 over Laplacian of B equals 1 lambda squared B, right? Let's mount some setup that looks like this. It's semi-space where half of the space, LED space, okay? Half of this space is a superconductor and half of this space is a vacuum. And we put a magnetic field perpendicular to this plane, tangential to this plane. Let's say we put a magnetic field like this, okay? Constant magnetic field. So outside in the vacuum, we will have constant magnetic field. Inside the superconductor, when you solve the equations, when you solve this equation like this, let's say we have some symmetry along the tangential plane. So along this plane here of the interface, we have symmetry of magnetic field. So we will have just B, second derivative of B equals 1 over lambda squared. Okay, let's put this in the z direction, for example. But this is function of x. Say this is derivative with respect to x. Okay. So the x direction is this one, and the z direction is this one. Right? So what we have this exponential decaying solutions. We'll have cannot be exponential increasing because when you go too far, it will diverge. It will become infinite, and we don't see infinite magnetic field, right? So we can cut the solution positive exponential and just keep the solution with negative exponential. This will be the solution. So if here's external magnetic field, right inside the superconductor, because of continuity, it should also have value, but then it should decay very quickly, and it decays to 0. This length lambda. This is why it's called penetration length, because the magnetic field only penetrates up to this length lambda. After this lambda, it's very weak magnetic field inside, exponentially decaying. Okay, and this is what explained the phenomenon, the Meissner effect. So this was big success of the brothers London, because with this theory, you explain why the magnetic field goes like this. It's because of the currents that appear, and these currents are diamagnetic currents, and they decay inside the superconductor exponentially. There's one tiny length of penetration where this magnetic field inside the superconductor, but then it goes out like this. Okay. Yeah. So I think I will stop here because what comes next is Ginzburg-Landau theory, and it's too much for today. So I will stop here. I think when is the time that we stop? It's at 2 or at 2:20. Let me see. But today should be just one, right? You stop at 2 or 2:20? 2:20, right? 2:20. Yeah. So what I could talk about, just to go in short details, because I think it's enough details. We don't need this bunch of equations. We will never use these equations. But the only point I would like to punctuate is that actually there are exceptions to this rule. Sometimes magnetic field penetrates superconductors, and these are a second class of superconductor. We call this type 2 superconductors. And actually, this was work by Abrikosov. This work was developed by Abrikosov. He worked with a theory called Ginzburg theory, and he actually found out that magnetic field can occupy some periodic lattice in the superconductor. So typically, they appear in thin films. Okay, so in thin superconductors, when you apply magnetic field, the superconductor is not strong enough to shield it out. You know, when it's a sphere, usually it's okay to shield the magnetic field. But when you have just a very thin film, it becomes too strong, the magnetic pressure, and the magnetic field can penetrate. But because this is a quantum material, some weird stuff appear there. So magnetic field just doesn't penetrate continuously, uniformly. It penetrates in a very weird way. It's this. It appears these points, this lattice of magnetic field. So, for example, if you have a film, let's make a side profile. If let's say this is your, okay, and you apply magnetic field perpendicular like this. This is your magnetic field. Okay. So what you will have is that eventually you will have some lines of field penetrating this. And this magnetic field around this lattice, it decays under the London penetration length. Okay, it's like this. I think I might regret not discussing Ginzburg theory because we will need this to understand the Josephson effect. I should probably talk about the Ginzburg-Landau theory. But it's just that I'm really feeling this is too much details, too much equations to talk to you guys. Okay, so let's just keep like this. So is that Abrikosov discovered this periodic lattice, okay, and magnetic field in type 2 superconductors. It does penetrate, right? Penetrates, and it's quantized. So the flux is here and occupies this 3D lattice. And this quanta of flux is called phi 0, and it's given by fundamental constant. So this is Planck constant, speed of light, and electric charge. Okay, and now the critical field of the superconductor. You can increase magnetic field until a point where superconductivity is destroyed. If this is type 1 material, you only have HC, the phase where the Meissner effect shields the superconductor. Above this critical field, superconductivity is destroyed. But now, in type 2 superconductor, after the Meissner phase, if you go higher fields, you will get the vortex phase. And the vortex phase, it goes up to the field HC2, which is much higher, okay? So in this theory here, if you look at the magnetization, right? Let's look at the equation for magnetization. Inside the superconductor, you have pretty much a magnetization. So let's put like this: magnetization equals minus. Yeah, I needed to mention more details, and I don't want to go into much details in this stuff. But anyway, type 1 superconductors, the magnetization is exactly the negative of your applied field. Okay, so if this is your applied field H, we call this H to differ between the local field and the applied field. This is the field I control. This is the experimental parameter I control. Okay, this is why we call H. So I control this H, and if this is type 1 material, magnetization increases until a point where you reach critical field, and then it drops down to 0. So you lost this superconductivity. You just destroyed superconductivity because magnetic field is strong. But if you have a type 2 material, what will happen is that when you apply the field, magnetization shields. This is the Meissner phase, right? So this here is the Meissner phase. And then magnetization will start decreasing after HC1. HC1 is the field that have penetration of vortices, right? So HC1 appears, and then this thing down until HC2, where magnetization is 0, and you go again for the normal phase. So these are pretty much superconductors. Some quick introduction to superconductors, okay? On the next seminar, we will go for how you can use superconductors to create quantum computers, quantum gates, and quantum bits, and so on. Okay. So, but to conclude today, we learn how to implement arbitrary binary functions in terms of keys, right? So this was first part of the class. Particularly, we learned how to build a quantum circuit to calculate sums, right? We created the adding formula, right? And then on the second part, we saw the introduction to the phenomenology of superconductors, right? And basic theory appeared, and all this, the magnetic behavior, electromagnetic behavior of superconductors, right? So in the next seminar, we are going to go for deep stuff, in superconductors and how to use them to build quantum gates. So thank you. I think this is enough for today. Yeah, I will share the presentation. Sure, sure. I will send to Valeria. She can send you guys. Thanks for coming. Thank for being extra time today. See you on the next week. Okay. Questions, comments? I think very interesting. I'm happy you liked. Great, great. All right. So see you next week. Take care. Okay. Bye.